Okay, so we're going to start at 3.1. 3.1 is very closely tied to 2.4. It's all about the derivative of a function, which is the slope of the tangent line at a particular point. So so that's what we're looking at, the derivative function, the slope of a tangent line. And we define it as this. Remember, m is slope, right? That's the letter we've used all along since you guys started doing algebra. And we have a weird expression. Remember, f of a is right here, a comma f of a plus h comma f of a plus h is right there. You have p and q. If you draw a line through those 2 points, that's a secant line. However, if h gets closer and closer to 0, as we know, so here's the limit, that actually gets us the slope of the tangent line, provided that the limit exists. And if it does exist, then we have a derivative at x equals a. So again, we call that the derivative, which is also called the instantaneous rate of change. Now, let's do a quick comparison. Give me 1 second here. Just gotta go to Dropbox, my other device. Lecture notes, fill out notes. That should be opening up in a sec. There we go. Yeah, so the average rate of change, again, we just expressed it like this. F of a plus h, ooh, it's a nice blue color, kind of turquoise, over a plus h minus a, which was really just f of a plus h minus f of a all over h. Whereas for the instantaneous rate of change, it was the same exact thing, both the limits. So this has no limit for h. Here is the limit as h approaches 0. So that's the difference between average rate of change and instantaneous rate of change. Average rate of change is just a very simple slope you find between 2 points. Instantaneous is when you find the slope of a tangent line. So you treat it as a limiting case. So that's just to sum up what we've done in 2.4. Okay, any questions so far? And again, the plans, we're going to go to we're going to do the first 2.5 pages. So we'll definitely do the first 2 pages and half of the 3rd page. That's the plan for today. Okay, let me keep moving. And I'll clear my screen. And again, if you have questions, feel free to put in the chat or speak into your microphone. Now, the next part is to help with notational fluency. It's all about notational. I really like this color. It's a really cool color. It's kind of like a, I was a North Carolina fan, like Tar Heels colors. So we need to make sure we're comfortable with the notation. And there's a lot of ways you could actually write this, the derivative, when I say this. So we create a function, f prime. So we call that f prime. And you see in the little accent mark. That's what we're going to use for the derivative. So we tend to call the derivative f prime. So I'll be using that often. So here, that's like saying f prime of x. No, we say f of x, we see f parentheses x. Now you see f accent mark parentheses x, we call f prime of x. And it's just what we've done in the previous section, right? The limit as h approaches 0 of fx plus h minus fx over h. Now in this case, we're using x instead of a. So the difference is that f prime of x is a function for the derivative. F prime of a is the numerical value of the derivative at x equals a. So f prime of x is kind of a general function for the derivative. So the outcome will be an expression. Where f prime of a is actually going to be a number. So I want to make sure we're clear about that. So what's being expressed in the box here is actually going to be an expression. Your output is an expression. Whereas what we did in the previous section, the output was a numerical value, a number. So that's what's being said here. We create a function f prime whose domain is those values in the domain of f, blah, 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 right? Whatever domain you have for f, you apply it to f prime, for which a derivative exists, with the corresponding output being that corresponding value of the derivative. So in other words, the output's going to be an expression. And we call it the derivative of the function f with respect to the variable x, because we're using the variable x. And remember, the limit has to exist for this to work. If it does exist, that means the derivative exists. And then we can say the function is differentiable. So we say this as long the limit, as long as the limit exists. What limit? That limit that right there. So we could say it's differentiable. So it's able to be differentiated, right? So, you know, it's kind of like if you're, I don't know, if something is readable. Sometimes my stuff's not that readable. You're able to read it. Or something's legible, like it's able to be legit, like you can actually say it's legitimate. I don't know if that makes sense, but this is so remember, it's able to be differentiated. A differential function is one that is differentiable at every point in its domain. And there's some notation that we have to talk about. So all these here they're all the same thing. They're all the same thing. Just different ways of writing they're all the derivative. So just different ways of writing the derivative. That's all. So here you could say f prime of x. So if you see that, you got to know what it means. It means the derivative of f. This, you could say y prime. That's actually my favorite. It's my favorite because it's easy. I'm lazy. So when I was in high school, I just did y prime. Likewise in college. As I got older, I've used more of the other notation because I have to encourage that. Sometimes it's, and actually sometimes it is more proper to write the ones that you see in the last three. Can I clear my screen, by the way? We're okay? Yeah, good. Okay, I'm going to clear my screen right now. Let me scroll down just a tad. Let me rewrite the stuff in the box here. So again, let me just kind of just do little partitions. So we say this is f prime of x. We call this y prime. Now this is kind of funny. We call this d, I'm going to write phonetically, dy over dx. So I'm doing DEE, dy over dx. This is say df over dx. Now, why does this notation exist? Like why the d and the f and the d and the x? That'll be more clear as we get further in this class. For now, just know it means a derivative. Okay, I'll explain kind of the rationale between the dy and the dx, like what's going, and that'll be made more clear later in this class. And then lastly, we say this is d dx of f of x. So this right here is thought of as a derivative, sorry, as an operator for the derivative. So we say d dx of f of x. Or you could say the derivative of f of x with respect to x. And the reason why I say with respect to x is that you see an x in the denominator here. This will actually be made more clear when we start doing something called implicit differentiation, which I think is in section 3.4. So it won't be to our third unit, where we start really embracing notation more deeply. So I'll explain why we have this dy and dxing when we get to 3.4. So that's more specific. So not probably until maybe the end of the month, we'll do that. Okay, so just notation stuff. Make sure you guys are comfortable with all that. Okay, so let's move on. Let's do an example now. So we're gonna do the same thing that we've done before in 2.4. So actually 3.1, 2.4 are almost identical sections. That's why I feel kind of comfortable kind of just keeping things moving and not really lingering, because it's not necessary. But this will help reinforce a lot of stuff we did in 2.4. So examples 1 and 2 are very, very similar. And we'll do example 3. And I'm gonna kind of stop right over here because the video starts over here. I made the video last night or yesterday afternoon, I think. Okay, so let's look at example 1. So you're asked to find, so basically, what is this asking you to do? Or that we call dy over dx. That's just the derivative. That's all we're doing. But the answer will be the answer will be an expression. Then there's a second part where they want to find the equation of tangent on x equals 5. We'll worry about that later. Let's do this over here. Now, remember, it's a limit as h approaches 0 of f of x plus h. Not doing f of a anymore. We're doing f of x plus h minus f of x all over h. So there's no a at all. No a. What is fx? X cubed. And you're x plus h cubed over h. You're still going to solve it the same way, just that you have another variable to deal with. You have x now to deal with. Whereas before we had, remember, we just had like a number. We had like maybe like f of 1 plus h or f of 1, whatever. So we are going to have to expand x plus h cubed. Now, in the little box here, I have a little hint. Remember, if you have a plus b cubed, you could just FOIL it 3 times, kind of like this over here, and then simplify it. But it's also, there's something called binomial theorem, which sadly we didn't cover with the Algebra 2 since last spring because of the pandemic. So we'll have to teach them pre-calc because they need to know it. If you know it here, great. If not, you can always FOIL. But this is part of the binomial theorem. The binomial theorem states that when you have something like this here, you do like n. I'm not sure if you guys remember like combinations. And then you do this. And you kind of keep going until you get 3C3. Again, I'm not sure if you guys remember that. That's how that was found up above over here. Or you can use Pascal's triangle to get the combination values. Not sure if you guys seen that. But that's how you can kind of streamline the expansion of binomials. Remember, binomial by two terms, a two-term polynomial expression. And if you expand it, like you have to multiply it over and over again several times, you could just more concisely do the binomial theorem, which will get your answer quickly. You start with a combination. It's usually like NC0, N is a exponent here, and then you keep going with like NC, 3C0, 3C1, 3C2, 3, until you get to 3C3. These can be computed in the calculator, just so you know, under Math, PRB, and CR. You'll see it right there. So just so you know, it's all in the calculator. Or in lieu of doing the combinations, you can also use Pascal's triangle to get those combination values. And it's just a repetitive process where you take the first term to the n power and the second term to the 0 power, and then you kind of do a trade-off. You keep dropping the exponent of the first term by 1, increasing the other one up by 1. All right, let's keep moving here. Okay, so let's expand this now. Now we know how to do it. It's gonna be x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed from this guy, right? All over h, the limit as h approaches 0. Again, can't get lazy, keep writing the limit notation. And what goes away? These should go away. If they don't, you made a mistake. Anything that doesn't have h must go away. Now, what's remaining up top? Every term has an h in it. Factor it out. If you factor it out, you get 3x squared plus 3xh plus h squared all over h. H's cancel. Plug in 0 for h. You should get 3x squared plus 3x times 0 plus 0 squared. Final answer is 3x squared. Now, for those who've had calculus before, you will be aware that there is a shortcut for doing this. The shortcut actually takes about 2 seconds, maybe even less. You'll not be happy when I show you the shortcut I made you do it this way, but I want you to do it this way because you have to understand the process of finding a derivative. So I'm going to ask that you do, and I'm actually going to look at the homework a little more closely to make sure you're doing it this way, because you really need to embrace this. But yes, we'll do a shortcut when we get to 3.3. So probably in about the end of next week or so, we'll probably have done the shortcut by then. And our next test, I haven't decided when that will be. Most likely, I'll probably do it the last week of October, just like I did for this test. I have to kind of see how the pacing looks, and I'll have that established for you guys. So that's what's happening there. The second part's asking you to find the equation of tangent on x equals 5. Well, at x equals 5, let me do that in blue. At x equals 5, y is 125. Remember, that's our function. So if you do point slope form, easy peasy. We know this, right? Now your slope at x equals 5 is just simply going to be this. The slope is going to be 75, because remember, this represents the slope of f of x, but it's represented as an expression now, 3x squared. So at x equals 5, plug it in, do your PEMDAS correctly, you should get 75. So that's going to be your slope. And we're just at x equals 5, so x minus 5 and y minus 125. So that's the second part of the problem. Find the equation of the tangent to the curve at x equals 5. Remember, the derivative represents the slope of the tangent. But because we did it as an expression, not as a numerical value that we did in 2.4, because we did a fx plus h minus fx, not f of a plus h minus f of a, we did f of x plus h minus f of x. It's actually more advantageous to do it the way I did it right now. So when you have a general expression for the derivative, like this right here, then I can plug in any x value I want to get the slope of the tangent at any x value. So that makes it actually better to do it this way. And then the second part, again, find the equation of tangent at x equals 5. Great. Plug in 5 into my derivative, which is 75. That's my slope. And of course, that when x equals 5, y is 125, and I have the equation of tangent. Now, there is a question. Do ask questions. Oh, how do I get from 3x squared to 75? Remember, I plugged 5 in for x. That's all I did. I plugged 5 in for x into the derivative. So remember, the derivative represents the slope. All this right here is the slope of the tangent line for f of x. But what we got, which is 3x squared, is actually a general expression for the slope of the tangent line. So use that general. I use that general expression to help me find this right here. So I plug 5 in for x because we're told to find the equation of tangent x equals 5. And then, of course, I have my answer. Again, the derivative of x cubed is 3x squared. That'll always be true. And let's just kind of take a quick, let's explore that just a little bit, just so you guys understand what's happening. If I go to Desmos really quickly, let me clear my screen. Y equals x cube. Oh, cube. So this graph is always rising. And what if I drew a bunch of tangent lines? Like, what if I drew a tangent line like here? Okay, that's a crappy line. I can do better than that. Like here. Or what if I drew one like right here? Or if I drew one like right here? Like at x equals 1, if I do 3 times 1 squared, I get 3. Here, this is like an x equals half. So I do 3 times 1/2 squared, which is 3/4. Here, that's at x equals 0. If I plug it into 3x squared, remember y equals x cubed, the derivative, which we'll call y prime, was 3x squared. Here, if I plug 0 into 3x squared, 3 times 0 squared is 0. That's a flat line. What if I could do something that's really steep? Like x equals 2, which I know is going to be, the y value is going to be 8. That's a very steep line, right? That slope's going to be 12. That looks like a slope of 12. That looks very steep to me. So those are things that we want to understand, is that the derivative actually represents the tangent for the original function, the slope of the tangent lines. And because we put it as an expression, we can plug in any x values into it to always get the slope of the tangent line at various points on the original graph. So that's something that we're going to be just doing a lot of this semester. Okay. Let me get my annotated feature away. Okay, let me clear the screen. Okay, let's look at example 2. And I'll do example 3. And then I'll let you guys get a little head start on homework. Okay, 1 over x. Let's find the derivative of that one. So again, you take a limit. Let me get my stylus here. Limit as h approaches 0 of f of x plus h minus f of x all over h. So it's going to look like this now. Remember, that's your function. F of x straight up knows 1 over x. Fx plus h 1 over x plus h. Okay. So your LCD is going to be x times x plus h. So you got to multiply this by x plus h and multiply this by h. I'll have you guys try that right now on your own. I'll give you guys about 2 minutes. After those 2 minutes are up, then I will kind of do it quickly and see if you guys got the same thing as I did.
Is it supposed to be times x instead of?
Oh my God, yes.
Yeah.
You know what, my daughter is crying like crazy, and so I'm a little distracted right now. I'm not sure if you guys heard in the background. So, there we go. Yes, you're right, XX. Thank you for catching that. Okay, so you guys should be getting this. Again, that's 0. So up top is going to be x minus parentheses x plus h. The bottom would be x times x plus h. And then all that is over h, which I'm going to write as h over 1. Because h by itself is h over 1. Anything by itself is always over 1. We know this. Distribute the minus. So you get x minus h. Careful there. X times x plus h. And because you're dividing by this fraction, I'm going to flip that over and make that 1 over h. Again, the limit is h approaches 0. These x's cancel, so you get negative h over x times x plus h times h, because you're multiplying the denominators together. And fortunately, those h's cancel. So you get negative 1 up top over x times x plus h. The limit is h approaches 0. Now I can substitute 0 for h. Negative 1 over x times x plus 0. That becomes negative 1 over x times x, or x squared. So the derivative of 1 over x is negative 1 over x squared. That's the derivative of 1 over x. Any questions? Please ask questions if you're unsure of the algebra. Now, sorry, it's negative 1 over x squared. It's a little hard to read. If I go to Desmos really quickly, just to reinforce this. So we always want to think of this graphically too, right? Let me clear my screen. 1 over x, right? So say, for example, I'm at x equals 1. And say I drew a tangent line there. That looks like a negative tangent line. Or say at x equals -6, I drew a tangent line there. That also looks negative, but not as steep as the one at x equals 1. Well, at x equals 1, remember my derivative was -1 over x squared. So if I plug that in over here, my derivative is going to be -1 over 1 squared, which is, of course, is -1. Here, be -1 over -6 squared, which would be -1 over 36. So that kind of makes sense again, graphically, what's happening. So we're trying to make all these connections now, right? The graphical and algebraic connections. So this kind of makes sense that this would be a great general expression to give me the slope of the tangent lines for 1 over x at different x values. Okay, clear again. Let's do the last example. Come on, here we go. So let's do it, excuse me, for root x. So let me set it up again, and I'll let you guys try it. So y prime is going to be the limit, or dy over dx, same thing. I like using y prime. That's just my preference. But dy dx, y prime, f prime, whatever, it's all the same. All mean the same thing. And I'm doing this for f of x plus h minus f of x all over h. Now remember, you can also write as f of x equals root x, right? Y equals root x, f of x root x, same thing. It's all interchangeable. Well, f of x is root x, of course. That's root x plus h. That's h. And that's the limit as h approaches 0. So again, we're doing the same thing we've done in examples 1 and 2. We're trying to find the derivative. That's the form for the derivative. The limit as h approaches 0 of f of x plus h minus f of x over h. And I said it really fast, but that's what it is. It's right there. F of x is root x. That's our original function. Replace x with x plus h. Now it's root x plus h. How are we going to find this limit now? Hopefully you guys remember the conjugate. We had this in our last test. That's what you got to do. You got to multiply top and bottom of that by root x plus h plus root x. I emphasize the plus because you have to have that sign change, because the whole point is for things to clean up top. I would not distribute the h on the bottom, just so you know. Definitely want to FOIL the numerator, but leave the denominator as the following. Because you're going to want that h to cancel eventually. Work it out. Again, I'll give you guys a couple minutes. I'll show you what I get. Then we'll do this parts in the starburst, and then we can talk about any question we have from the problem sets that we have from homework. Okay, I'll do this quickly. So you guys get the same thing as I do. Okay, so if we FOIL correctly, let's do some blue. Should be getting this. This times this is x plus h. This times this is, you could write it as positive root x times x plus h all underneath one radical, because you have x and x plus h being multiplied. And then this and this is negative of that same radical. So naturally those will cancel. And then of course that's negative root x times root x, which is going to be negative x. And the bottom leave as is, right? Don't mess with that. Now here's the nice thing. Those x's cancel. These cancel. You just get h up top. It actually comes out that nicely. So you have the limit now is h approaches 0 of just plain old h up top and h root x plus h plus root x. H is canceled here. Now I can plug in 0. It's 1 over root x plus 0 plus root x. That's 2 root x's on the bottom, and that's your answer. 1 over 2 root x. And actually, that should be in the starburst there. That's why the starburst was set up. So derivative root x is 1 over 2 root x. That just is what it is. Again, if you were to graph y equals root x, say that x equals like 16, I know y is 4. There's my slope. If I plug 4 into that, I would get 1/4 as my slope, which looks like it's about 1/4. If I did it a little earlier for x, like at x equals 1, I think my slope would be 1/2. So we see the slope does get a little less shallow. Sorry, a little less steep as x gets bigger. And 2 more starburst results we filled in after homework on 3.1. I'll just kind of tell you what to expect for these next 2 bottom ones here. That is a line. We know this. It's a linear function. Well, if you have a line, the slope of the tangent line is the slope itself. So it's just going to be m if you were to work that out. Here, x squared is going to be 2x if you were to work that one out. Y equals x squared is this. If I drew a bunch of tangent lines, say that x equals -1, that's a negative slope, but x equals +1, it's a positive slope. So that covers, as far as I wanted to get to with the 3.1 notes as a live lesson. There's a video lesson for homework that's already in Schoology. The Google form, actually, I have the link. I just have to finish making the questions for it. I'll do that, probably do that during my break between this period and B period. So the homework will actually be, it's actually ready. So it's up. The video's up, but the Google form is not quite prepared. The textbook problems I already have prepared. The textbook problems, let me show you really quickly what's happening with that. Any questions so far? No? Okay. So let me stop this recording.